sigma square t. Okay, mu t. So it's going to be mu plus sigma square t square by 2, and then if you substitute t equal to 0, this will become 1, and you're going to get what you call mu actually. So it's going to be e to the same function times mu plus sigma square t. Okay, and then if you substitute zeros, you're going to get e to the 0 times mu plus 0. So that will be equal to the mu, which is really the mean of the normally distributed random variable. So I would suggest that using this moment generating function, try to verify that really the mean and the variance of the normal distribution are really mu and sigma square actually. Okay, so that's an alternate way to do the computation. Now let's do some examples. Let's prove some of more interesting results. So how about if you have two independent random variables and you want to find their moment generating functions actually. Okay. So the next calculation that I would like to do is really the example 7f, and this says that if x and y are independent, okay, then what is the moment generating function of x plus y? Okay, the moment generating function of x plus y. I can calculate the moment generating function of x plus y t as what? That this is equal to the expectation of t times the random variable x plus y by definition. So whatever random variable you have, t multiplied by that random variable. Okay. So I can write this as expectation of e to the tx times e to the ty. Now we know the result that if you have expectation of g of x times f of x, f of y for example, where x and y are independent, then this expectation, and g and f are say continuous actually, then this expectation is equal to the expectation of g of x times expectation of f of y. Now I know about my x and y that they are independent, and e to the tx is a continuous function of x and this is a continuous function of y. So this is like this situation actually. So these two must also be independent. So if they are independent, I can say that okay, this is equal to expectation of e to the tx times expectation of e to the ty. Okay? And what is the expectation of e to the tx? So this is the moment generating function of x at t times the moment generating function of y at t actually. So what does this shows? That if you want to compute the moment generating function of sum of two independent random variable, it is simply the moment generating function of the products actually. Okay? So the moment generating function of sum of two random variables is moment generating function of the product actually. Okay, so this is simple. You can even generalize this actually. That instead of 2, say you have n random variables. So instead of 2, say I have n random variables. I have random variables that goes from, so I have for example a random variable say an x, okay, where x is a sum of I equal to 1 to n xi, okay, where these x1, x2 up to xn, they are independent, okay, they are independent. So what would be the moment generating function of x of t? So it's going to be the moment generating function of the product of the moment generating function of these actually max of t of 2 up to xn of t. So you can easily show through induction that this is true in general, that the moment generating function of the sum of independent random variables is equal to the the product of their moment generating functions. Okay. Now, let me write sum that goes from hyper to x. Okay. Now imagine that so this identity is true in general, but in this assumption that x1, x2, say up to xn are independent, now you assume that they are independent and identically distributed. Okay? They are independent and identically distributed. They have the same distribution actually. So the expectation, x1, x2 and xn, they follow the same distributions here. So their expectations are really same actually. The expectation of xi, xj is really a fixed number mu. Okay, really a fixed number mu actually. Okay, the question is then what would be the moment generating function for such functions actually if their expectations are true. Then what will happen if this is the case? If the expectation of xi and xj is equal, my claim is that the moment generating function of xi of t is the same as the moment generating function of xj of t actually. Okay, so if the random variables are identically distributed, their moment generating functions are also equal. Why this should be the case? Here's the thing. So take say xi of t, I know that this is going to be the expectation of t xi. Okay, this is going. Now since they are the random variables are identically distributed, okay, it is not difficult to see that this expectation, whether it is discrete or continuous, is equal to the expectation of t xj. In other words, this is going to be, if you compute this expectation, is going to be e to the tx multiplied by the PDF of xi and e to the txj multiplied by the PDF of xj. But the PDF of xi is equal to the PDF of xj actually. So they are, they have the same PDF because they are identically distributed. So therefore these expectations should be equal actually. So this should be equal to mxj of t. Okay, so I'm just giving, if I wish, I can write it a bit more explicitly. Okay, I can write a bit more explicitly. I can say that okay, expectation of say e to the txi is going to be the integral, for example, continuous time case, e to the tx times the PDF of xi of x dx. But xi and xj have identical distribution, so they must have the same PDF. I can say this is same as e to the tx times fxj of x dx. So this is same as expectation of txj. So you get that? So this means that if you have a number of random variables that have identical distribution, okay, and you want to compute, for example, so their moment generating functions is also going to be identical. Okay, their moment generating function is also going to be identical. Now, what if I want to calculate the moment generating function of some of these xi's of t? Now, for xi, I know that they are independent and identically distributed. Now, since due to the independence, you're going to say that, you know, the moment generating function of the sum is going to be the product of the moment generating functions. But I know that all these moment generating functions are equal actually. It is one and the same because their moment generating functions are same actually. So if this is the case, then I can say that, okay, this is same as moment generating function of say x1 of t, moment generating function of x1 of t. So it's like moment generating function of x1 of t power n. Okay, because all these numbers are same actually. Okay. So if you have i.i.ds, the moment generating function of the sum is equal to the, take any one moment generating function of any random variable and take power n. Just simply multiply them. Why? Because that in case of i.i.d, moment generating functions are equal to each other. So this is like, okay, it's the same number multiplied n times, so it's going to be power n. Okay. So I hope this is making a little bit of sense to you. I would suggest that you should do example 7J from the book as well. I'll post the list of examples as well, which you should do in order to have a better understanding of all this stuff actually. Okay. Now we can move to the new section. This is almost the last section actually. That what would be the moment generating function of the joint of the random variables actually, a joint moment generating function. So if you have two random variables, what would be the moment generating function of their joint? The answer is, it's not difficult to say actually. So joint moment generating function. Okay, this is what that I would like to say. So imagine x1, x2 up to xn are some, random variables, not necessarily independent. Then the moment generating function of the joint is going to be a function that not going to depend on, for example, one quantity t, but it's going to depend on n quantities. So m of t1, t2 up to tn is equal to, so you define this as the expectation of e to the t1, x1, t2, x2 plus so on and so forth plus tn xn. Okay, so this is really the moment generating function of the joint actually. Okay, and you can so in order to compute the moment generating function of joint, for example, if I am saying that, okay, what is the moment generating function of joint of say two random variables x and y? So I'm going to say that, okay, it's going to be function m of 2. So if you have two random variables, what would be the moment generating function of it? So it's going to be equal to the expectation of e to the tx plus s to the y axis. This is going to be the moment generating function of x. Okay. As we know about, for example, that if you know the joint PDF, you can compute the individual PDFs of what do you call each random variable, what do you call the marginal PDFs. The question is, can you have something similar here, that if you know the joint moment generating function of the random variables, then can you find the moment generating function of say individual random variable? The answer is yes actually. So imagine you know this, just compute it at say 1, 0, 0, say 0. Compute it at 1, 0, 0. So what would be the output from here? So it's going to be, for T1 is T2 is 0 up to Tn is 0, so it's going to be e to the, say, T1 instead of 1, say, says we substitute Tn, okay, T000. So it's going to be e to the Tx plus 0, 0, 0. So it's going to be expectation of e to the Tx, and the expectation of p to the x is the moment generating function of say x1. So similarly, you can compute the moment generating function of any random variable if you know the joint moment generating function. Okay. What would be the joint moment generating function if you know that x1, x2, xn are independent? So if x1, x2, xn are independent, what would be the joint moment generating function of this? So you're going to say that, okay, m of t1, t2, tn is going to be the expectation of t1, x1, t2, x2 plus tn, xn. Okay, this is what it is going to be, plus tn, xn. This is what it is going to be. But then I can write them also as the expectation of T1, x1 up to Tn, xn. And by the same previous argument, since x1, x2, xn are independent of each other, so they are e to the tx1 and e to the tx2 up to the e to the txn, they will be also independent of each other. Hence, this would be equal to the expectation of e to the t1 x1 times e to the tn xn, which is same as the moment generating function of x1 of t multiplied by the moment generating function of x2 of t multiplied by the moment generating function of xn of t. So this is what that you can get. So for the joint PDF, so if you know xn, x1, x2, xn are independent, their joint PDF is simply the product of the PDF, like the CDF and like the PDF and CDF actually, joint PDF and joint CDF. Okay, the same is going to be the case. So here's a little interesting example. So it is a little interesting example. The little interesting example is that, okay, so if x and y are normally distributed with u and sigma square, okay, and they are, it is known that they are independent. So they are independent and they are normally distributed with mean x square and y square. Compute moment generating function, joint moment generating function of x minus y and x plus y. Okay. What is the joint moment generating function of x minus y and x plus y? What are you going to do? You're going to say that, okay, the joint moment generating function of x minus y and x plus y evaluated at, for example, times s and t is going to be expectation of s times x minus y plus t times x plus y. Okay, and you can play a bit, and I can write this as, for example, expectation of s plus t x times x and plus t minus s y. Okay, this is what that you can do. Okay, and I can also write this as expectation of t plus s x times expectation of t minus s y. And by the same argumentation, I can say that this is same as expectation of t plus s x times expectation of t minus s y, because x and y are independent. And this is same as compute the moment generating function of x at t plus s and compute the moment generating function of y at t minus s. Okay. Now, what is the moment generating function of normally distributed random variable? We know that the normally distributed, if a random variable is normally distributed, its moment generating function is mx of t is mu t plus sigma square t square upon 2. So by this definition, the moment generating function of x evaluated at t plus s, so replace t by t plus s. So the first is going to be e to the t plus s mu plus sigma square t plus s square upon 2 times e to the t minus s mu plus sigma square t minus s square upon 2. Okay, and if you simplify this factor, okay, you can put them together and do all cancellation and all that stuff. So you're going to get e to the 2 mu t plus sigma square t square times e to the sigma square s square. So this is going to be the moment generating function of x minus y and y minus x, which we calculated through this strategy that we just proposed actually.